Hey everyone, I'm Tiffany from SigOpt. Thanks for joining us today on tuning for systematic trading. So last session, we focused on scaling tuning jobs with parallelism and multitask optimization. Today, we're going to continue to build on that by discussing metric strategy, monitoring convergence, and automating early stopping to efficiently tune your deep learning models. So here with me is Tobias Andreessen. Tobias is our machine learning engineer who works directly with a number of our systematic trading customers, and he'll walk you through the session. So we also have some time at the end scheduled for Q&A. If you have any questions throughout the session, feel free to drop it off in the Q&A box and we'll get to it at the end. Now I'll have Tobias take it away.
Perfect. Thank you very much. Hey everyone, and thank you for joining. I really appreciate you taking the time. As Tiffany mentioned, this is the third talk in our series around tuning for systematic trading. If you're interested in seeing the previous one, you can go onto YouTube. I also think we will be sharing links after this presentation when we send out the slides. So what we did in the past was talk about things like black box optimization in general, how to solve the problems, multitask optimization, parallel optimization, kind of from a very theoretical point of view. Today we'll be shifting gears, and instead of talking about the theory going into these things, we will try to talk about the applications and how you can think about it in your own work. So let's get started. I tried to come up with a bit of an abstract. SigOpt provides an extensive set of advanced features which helps you, the expert, save time while increasing model performance via experimentation. Today, we'll continue this talk series by discussing training, tuning, and metric strategies in the context of SigOpt, and use this to come up with a recipe for how this can be used for model experimentation. Excuse me. So, as always, I'll start out by giving a very quick overview of SigOpt. Again, SigOpt, we have a vision, which is to accelerate and amplify the impact of models everywhere. That means what we're trying to do is help you to do your job better and faster. And in order to do so, we built a solution or a platform that kind of sits over three different pillars. We have the experiment insights, which is where you draw information from the experimentation you've been doing. We have the optimization engine itself, and we have the enterprise platform. As I said previously, a lot of things we talked about was kind of in the realm of the optimization engine. So multitask optimization, multi-metric optimization, things like that. Today, we'll try to talk about the experiment insights and the enterprise platform and how you can use that to improve your modeling, whether you're doing trading, sort of more classical trading, you're doing machine learning, deep learning. I hope you'll be able to kind of follow along and project this onto your own projects. At least that's a goal from my side. And I hope that you will leave and have learned something that you can go and apply instantly. So I tried to come up with a name for this, and I decided on experimentation recipe. This is not a recipe that is one size fits all. This recipe made sense to solve this problem that I'll show in a second. Maybe you'll be able to use some of the aspects in your daily work. Maybe you want to go and change some things, or maybe you just want to say, oh, that makes zero sense for what I'm doing. That's perfectly fine too. So again, this is kind of where it all started 3 months ago. We're talking about black box optimization, because at the end of the day, what we do at SigOpt is black box optimization. So now, instead of talking about how to solve these problems using, surrogate models, acquisition functions, etc., let's talk about how you can actually directly apply black box optimization to your modeling workflow through this recipe that maybe not work for your problem. Excuse me. And the first thing to do when using SigOpt, at least that's what I prefer, is have some sort of project hygiene, because I don't think it's possible to just come up with a model, optimize this model, and you have the perfect results. as I'll be showing now, you'll probably need to go through a few iterations in order to gain the insights that you need in order to figure out, okay, what is success for me? So a good way to do that is by creating a project. That's always a good place to start out. In order to do that, you need your unique API token, you need your client ID, and you need some name. For the purpose of this presentation, I've chosen a name, Quant Series. And as you create this project, this pops up on the web dashboard they provide. So now you have one location where you're storing all your modeling. But the good thing is, this is not just for you. This can be for your colleagues, your clients, your managers, and so on. So it's a way for you to share what's been going on throughout this experimentation process. And at the end, I'll show why this makes sense. The next thing to think about is your data. Again, as we talked about around 2 months ago, everything that sits to the left of this, what we call the firewall, that's where you're the expert. That's where you make all of the decisions. Everything that sits on the right, that's where we hopefully are the expert. That's where you do the Excel optimization. We help you, create better models. So again, as I said, I've not chosen a use case from trading for a lot of different reasons. I've chosen a very classical machine learning example, which is, are we able to predict if a cancer tumor is benign or malignant? And I've chosen this simply because there is a really nice API in the scikit-learn library that allows me to pull in data really quickly. And also because this is a slightly imbalanced data set. Because as you can imagine, when you're sitting on industry or sitting at your trading desk, chances are the data is pretty noisy, the data is pretty messy, and oftentimes very imbalanced. So I figured it would make sense to take a data set which has some of these properties that you would probably find in the real world. And later on, I'll show how to kind of handle some of these issues that comes up. The next thing you should think about is having some sort of evaluation framework. Again, the most simple evaluation framework is most likely having, computing your accuracy for some prediction, some classifier. If you're working with this imbalanced data set, laying something like your F1 score, precision recall, maybe makes sense. Or your evaluation framework can be, some sort of backtesting engine that sits with you or sits somewhere else in your organization. We don't really care. All we need is this engine, whether it's coming up with some score of accuracy on a holdout set or market simulations. We just need the output of those, something that represents success. So the next thing when going through this modeling recipe is trying to figure out, okay, what are the metrics that represent success? And then inform SigOpt, I have these 4 metrics. I'm interested in maximizing all of them. I'm interested in optimizing my accuracy, but I just need to store my F1 precision and recall because that probably paints a picture of what's going on. Just as some information that I'll maybe need in the future. Again, all of this sits with you. This is just an example that makes sense for this particular data set. And the last thing in order to do experimentation is having a model. I'm personally a firm believer in coming up with baseline models is a really great idea for a lot of different reasons. Simply because, oftentimes you actually end up solving your problem using your baseline model, and it's a lot quicker, it's a lot faster, and it's a lot more computational cheap to use, let's say, logistic regression over a deep neural network. For the baseline model for this classification project, where I'm trying to predict whether a tumor is malignant or benign, I'm just using a simple logistic regression. And again, I'm using the scikit-learn API because it's easy, but there is a few things that you need to think about. And that ties kind of back to the experimentation for SigOpt. Obviously, you need to come up with a name for your model, but you also need to come up with a budget. Because as we talked about some time back, or a few months back, in this notion of black box optimization, you don't really know the function you're optimizing. All you can do is really observing the outputs, see how these different parameters affects the output. And the budget refers to the number of times you're going through this optimization feedback loop. The next thing you want to specify is sort of the parameters that goes into your model. Again, because this is my simple, very, very simple baseline model that I used to just get a feel for what's going on, I just have a simple parameter, a single parameter, which is the regularization coefficient or the C parameter, whatever you want to call it. And one thing to notice here is because I only have one parameter, doing some sort of Bayesian global optimization in order to come up with the best possible value doesn't make too much sense. So I'm simply just doing a grid search over this baseline model to figure out what's going on. Now we have thought a bit about, okay, what are the parameters, what are the metrics, what are the models that I really care about? Now, let's try to put it all together, because before you saw that we could create this this project. Let's try to take the experiments and put them into the project. And let's try to do optimization. So the first thing you want to do is create the experiment. Sort of what you're doing here is you're saying, okay, I want to do this grid search, put this experiment into this project. Here is the name of my model. These are the parameters, this single C parameter that I showed. And these are my 4 metrics. At the end of the day, that's all the information that SigOpt needs from you. We don't care about your data. We don't care about your evaluation framework. We don't care about your models. All we care about is the metrics and the parameters. And you can do whatever naming, whatever transformation you want so that we get 0 visibility into it. After you have created this experiment, what you need to do is start up this optimization feedback loop. And again, I showed some months back how we actually solve these problems, but from an application standpoint, all that really happens is that you say, okay, SigOpt, give me one suggested set of hyperparameters. Give me one value of this C parameter. You put that into your model, you train your model, and you return the objective metrics back to SigOpt. That's really all there's to it. And when you have gone through this, or as you're going through this feedback loop, you can go into the web dashboard and get a feel for what's going on. Now this experiment have completed, and we're able to look at sort of the the best set of parameters given this naive grid search we did over this one parameter. And there is a lot of information we can draw from here. So let's have a look at it. First of all, we got an accuracy of 94%. That seems reasonable. We got a reasonably well, if one score precision recall. Then we could say, okay, we're done. We were able to get decently good results on these academic metrics. Chances are, if you go up to your manager or your client or whoever you're working for and say, oh, I got an accuracy of 94% on this problem, trying to predict whether a tumor is malignant or benign. Hopefully the person will say, okay, that's great, but what does that mean in terms of being able to actually look at these tumors? You can make different arguments from looking at these different scores, or you can say, to be honest, I do not really know. So one of the nice things about the SigOpt API is that we allow you to store as many metrics, or not as many metrics as you want, but a lot of metrics, not for the purpose of optimizing, but for the purpose of just storing information because it's nice to have, and maybe you will need it to convince someone that the mod you created is indeed the best to bring forward into production. So let's say we went back to our evaluation framework and added two more metrics, which were how many of the benign samples did we get correct, and how many of the malignant samples did we get correct, and try to do this grid search again. Now we would get a lot more information. Some information that actually tells something about the business problem we're trying to solve. Because now you can see, oh, for the benign samples, we're actually doing pretty well, 96% of them we're getting correct. Whereas for the malignant samples, we're only getting around 90%, which means that 1 out of 10 we're not getting correct. Maybe that's okay for the purpose of this modeling project you're doing, but at least now you have the chance to go up to your manager, your client, and say, okay, this is how well I'm performing on these metrics that actually mean something to your business. Again, this is most likely some doctor, but I hope you're able to project this project onto something you're doing yourself. And these people can now have a look at it and say, oh, this is not great, because in order for me to actually use this tool in my clinic, I need to be able to predict the malignant sample correctly at least 94% of the time. Whereas for the benign samples, it's okay just being around the 90. And you can say, okay, that's great information, because now I have even more information I can put into my model. And let's show how that's done. Or let's do one more thing, because what you could think was, okay, I have an accuracy of 94. Let's say I just came up with a more complex model that got a better accuracy. Would that lead to a model that could go into production, giving these constraints that I got from the business side? Maybe that would be the case, maybe not. But anyway, let's try to be more intelligent about it. And start out by going to the analysis page and get a feel for the correlation across the different samples of these benign and malignant samples. Oh, sorry, benign and malignant values. Each of these dots represent a suggestion or an that you have trained, evaluated, and returned the observation back to SigOpt. And you can argue a lot of things here. I will choose for the purpose of this example to argue there isn't really any correlation between between whether or not we're good at predicting benign or malignant. So let's see what we can do about that. And one very nice feature that we have developed is what we call metric constraints. Metric constraints allows you to put constraints on these unoptimized metrics. Again, this is different from constraint optimization within the convex realm or convex optimization realm. This is simply you saying, oh, I have this unoptimized metric with me trying to predict how good I am at looking at these benign samples and the malignant samples and say, okay, I have these business constraints. Let's add them to these metrics. Again, these are not the metrics you're trying to optimize. This is just think of it as guardrail metrics. Saying, okay, from a business point of view, I need to beat these thresholds while trying to still optimize my accuracy. So think about what we just did. We started out by saying, okay, I just want to look at the accuracy in the F1 score. Everything looked fine. Then someone somewhere in the business side of things said, oh, I can't really use this information to draw in conclusions. Try to add more metrics that tell something about the business side of things. We did that. we came to the conclusion that our model is not good enough because there is constraints on these business metrics. Now, the last thing we did was say, okay, let's try to guardrail our optimization process by these constraints. And the important thing to also notice here is we have done nothing to our model. We've done nothing to our data. We have simply been looking at, all the way up to this point, we've been looking at our evaluation framework. An evaluation framework which just takes in predictions. These predictions doesn't care if this evaluation framework doesn't care if the prediction comes from a deep neural network or a simple logistic regression. It just tells something about the business metrics that we have and whether or not we're able to meet the thresholds. So the reason why I continue to emphasize that you need to do baseline modeling is because now we could very, very quickly figure out what is it that we need to see in order to drive our business forward. And I hope you're able to project, again, I hope you're able to project this onto projects that you do. Anyway, now we have built a framework for evaluation that really meets expectations of our manager or client. And let's start to talk about more complex modeling. Again, the evaluation framework, the data, that doesn't care if we were to do, logistic regression or deep neural networks. So let's just change the underlying model. Let's try to, for the more advanced modeling, do a neural network. Now, there is a lot more complexity going to neural networks, as you can imagine. But again, it kind of follows the same structure. You want to give it a name. You want to give it a budget. Again, this budget was the number of times you were going through this feedback loop. And because a neural network does not have a unique solution, you want to rely on some sort of gradient descent method. That's why you're doing these, epochs where you're essentially training your model. Again, this is not the scope for this presentation. So just assume we're doing stochastic gradient descent and we have to go for a number of epochs. Again, you have to be smart about setting the observation budget, setting the number of epochs. I believe that doing 40 epochs seemed reasonable. And the next thing you want to do is define, okay, these are my parameters. And in this neural network, I want to look at the number of nodes in the layer, like in the middle layer. I want to come up with a good learning rate, and I want to find a batch size so that I can maximize performance of my model. And again, now I'm using the Keras API. It's, it requires a bit more code, but it's pretty straightforward, somewhat similar to the scikit-learn API. Again, I'm just creating some modeling class that takes in, first of all, the assignment with these parameters, but also some data. And the data doesn't change, and nor does the evaluation framework, which is kind of the beauty of this. So as we go to do the optimization loop, this is where we do real optimization, because now we actually have a lot of parameters, and it makes sense to be smart, because oftentimes neural networks are, they take a lot of time to train, it takes a lot of compute. And the faster we can get good performance, the faster we can get models into production. Again, you start out by creating an experiment, say, okay, I have this project, this is the name of my model, I have these 3 parameters, I have my observation budget, and the things that differs from before is now you specify, okay, I know that I can go through up to 40 of these checkpoints or epochs. We didn't want to call it epochs because you can think of other models that relies on some sort of descent technique. And you ship all of that information to SigOpt. Now you've created what I believe to be the 3rd experiment in your project. This is where you start to do complex modeling. And in terms of the optimization feedback loop, there is one more thing that you need to add. And that is this inner loop you see down at the bottom, where you're saying, okay, please give me a suggested set of hyperparameters, put it into your model. Now do 1 epoch, return the metric values back to SigOpt, then do another epoch, do the same all over. Because now you can go into the web dashboard throughout time, monitor the convergence of these models as they progress. Again, as you go into the dashboard, yeah, now we've finished the observation, the experiment. We can start to look at, again, this is the best observation. We see, oh, now we're actually doing really well on the on looking at malignant samples, and we're also meeting the thresholds on the benign samples, because what we did was, with these constraints or these guardrail metrics, was to say, okay, optimize my accuracy or maximize my accuracy as much as possible under these two constraints, meaning I don't care about the best possible accuracy if I'm not meeting my constraints. Still, you're reporting that back to SigOpt so that we can get the information, use that to improve our modeling. But you're specifying, hey, I do not want a point that is not, I do not want a model that's not meeting these business criteria. And another nice thing is that now you can actually see the learning curves of these models. And you can argue whether or not this particular learning curve looks nice. At least you have the information, you can use it to decide whether or not this is a great model to bring forward into production. Again, this is a feature we call training monitor, where for models that rely on some descent method, you can monitor convergence throughout time. So you constantly know how all of these models are performing as they're trained. Let's say you're doing parallel optimization, training 100 models at the same time. It's actually pretty nice to know whether or not anything is working, especially in the beginning. So that's a nice feature to have. And if we go into the analysis page, you see the convergence for the best models, but we're also able to go back and look at these guardrail metrics and see, oh, we are doing a lot better on these malignant samples and still meeting the thresholds on the benign. And now you as an expert can go and say, okay, maybe it's not the model that has the overall best accuracy I want to put in production, but the model that slightly better on the malignant samples. Oh, sorry, malignant predictions. Again, this is not a finance example for a lot of reasons, but I do hope that you're able to look at this example and kind of, again, project it onto your own projects, because obviously you have some sort of metric that you want to maximize. But oftentimes, the business side of things have these requirements that you want to meet. And now that you have these requirements, let's be smart about doing the optimization so everything goes faster and you are able to look at more points or more good results in the feasible region. So I kind of hope that makes sense. And I know we are right on time. I'll be done in 30 seconds. Because the last thing I just want to show is that, as you can imagine, maybe you don't want to go through 40 epochs for every single model. That's why we allow you to just put in early stopping criteria, whether it's something that you have kind of homegrown, or you want to use some of the stopping criteria we have in SigOpt. But basically, it's a way for you to save time by saying, oh, I'm seeing something on this learning curve, let's just stop it. That's was the last thing I wanted to point out. Didn't really work so well for this example, but maybe it will for yours. Just took the most naive stopping so I could find. Oh, one last thing. As you saw before, I created this project. We have been throwing all of the experiments we have been creating into these projects. So now, as we go into this project, and as you hand off this project to client managers, whatever, you have these 5 experiments that you created in order to get these results. And you can, you can come up with this, I guess coming up with a story is not the right thing to say, but you can draw conclusions and make arguments for why you did what based on these different experiments that sits in this project, and hopefully that'll be enough for this model to be brought forward to production, or next step in the evaluation process. So I know that this was a lot of content really quickly. So again, we're over time. I really appreciate you all taking the time. I know it's very hectic times, but seems like every time we meet, everything is a little bit better. So hopefully that that continues. For those who have to drop off, that's perfectly fine. Otherwise, I can see we have a few questions. So if you have time to stay for just a few more minutes, feel free to do. And again, I really appreciate you taking the time. Thank you.
Thanks, Toby. So we do have some questions from the attendees. So the first question is, how many different metrics can be included in the experiment and what are the types?
Great question. So there is, I would say, 3 different types of metrics. There is the metrics you want to optimize. Here you can include 2. That's where you want to maximize performance. And there is the these guardrail metrics where you want to put in these business constraints. Here you have the option to include 4. And you have all of this information, which is just, all of this metric that just gives you information. And here you can include up to 50. So I guess that leaves it with 56 metrics in total across 3 different types. So yeah, that's the answer.
Cool, thanks for that. We have one more question. So can I apply constraints to metrics that I'm optimizing and how does that work?
Great question. And the answer is no. So you cannot apply constraints to those metrics. That constraints only sit on these guardrail metrics, but we have another concept which we call thresholds, which serves the same purpose. So you put in thresholds on these metrics that you want to optimize, but basically saying, oh, on my accuracy, I need to be above 80 in order for this to even matter. Because now you're simply just giving us information about your modeling. Because again, when we start out optimizing some model, we don't know if success is 5% or 90%. But by you saying, oh, I need to get at least 80, we know where to quote unquote start, where we start to see results, which is somewhat satisfying. So the answer is you cannot apply constraints, but you can apply thresholds.
Awesome. So thanks, Tobias, for leading a wonderful session. And then thank you to everyone else who joined us today. We're going to follow up with the slides and the recording. So our next session is going to be on Tuesday, June 16th. Stay tuned for more info, and I hope you could all join us again. So if you have any questions later on, feel free to reach out to us as well. Thank you.
Perfect. Thank you so much, everyone.